There are moments in science when confidence turns into uncertainty almost overnight. When instruments we trusted to extend our vision into the cosmos begin returning something we didn't fully prepare ourselves to interpret. That moment feels like it has arrived again. Not because the universe has changed, but because our ability to see it just took a leap we are still trying to emotionally catch up with. A new space telescope has begun returning images that are already reshaping how astronomers think about structure, scale, and even the hidden architecture of reality. The Euclid Space Telescope was designed not to zoom in on single spectacular objects, but to step back and map the universe as a whole system. Positioned at the Lagrange 2 point, about 1.5 million kilometers from Earth, it observes vast regions of sky in extraordinary detail, building what will eventually become one of the largest three-dimensional maps of the cosmos ever created. But what is emerging from its early data is not just visually stunning. It is conceptually unsettling. Euclid is not simply photographing galaxies. It is revealing how they are arranged, how they bend space, and how invisible matter silently governs their motion. Every frame carries two layers: the light we can see, and the gravitational influence we cannot. Together, they form a kind of cosmic blueprint, one that looks far more complex than expected. In its first major release, Euclid captured a mosaic covering hundreds of times the apparent size of the full moon. Within that limited patch of sky, millions of galaxies appear, stretching backward through deep time. But this is only a fraction of what will eventually be mapped. Even at this early stage, scientists are confronting a strange realization. We are not looking at isolated galaxies floating in space, but at a structured system woven together across unimaginable distances. One of the most striking early insights comes from dense galaxy clusters like Perseus. Within these regions, Euclid has identified not only large, well-known galaxies, but also hundreds of previously unseen dwarf galaxies hidden in the background glow. These faint objects matter because they respond strongly to dark matter's gravitational pull. Their shapes and distributions act like tracers, revealing where invisible mass is concentrated. What is emerging is a picture where dark matter is not a peripheral influence, but the foundational framework around which everything else forms. As Euclid expands its survey, a much larger pattern becomes impossible to ignore. Galaxies are not randomly scattered. They are aligned along immense filaments, cosmic threads of matter stretching across hundreds of millions of light-years. These filaments intersect at dense nodes where galaxy clusters form, creating what scientists call the cosmic web. But seeing it at Euclid's resolution makes the structure feel less like an abstract model and more like a physical reality. It resembles a vast interconnected network, almost neural in its complexity, as if the universe itself has a built-in architecture guiding how matter flows. What makes this even more striking is that these filaments are shaped primarily by something invisible. Dark matter does not emit light or interact with it in any direct way, yet its gravitational influence defines the entire cosmic structure. Galaxies form along its contours, not independently of it. In Euclid's data, this relationship becomes visually undeniable. Luminous matter is simply tracing a deeper unseen scaffolding. Gravitational lensing adds another layer to this picture. By measuring how light from distant galaxies bends as it passes through massive structures, Euclid can map where dark matter must exist. These distortions are extremely subtle, but when combined across millions of galaxies, they reveal something extraordinary. The universe behaves like a vast lensing system shaped by invisible mass. In some regions, light does not just bend inward as expected. It appears to distort in more complex, sometimes counterintuitive patterns that hint at structures not yet fully explained. Even more unsettling are early hints that the expansion of the universe might not be behaving exactly as expected. By comparing galaxies at different distances, Euclid effectively looks back in time. What it suggests is that large-scale structure may have formed earlier and more rapidly than current models predict. Galaxies appear to have clustered efficiently in the early universe, guided by dark matter in ways that may not fully align with existing simulations. This raises questions about whether our understanding of gravity and cosmic growth is complete. At the same time, Euclid reveals enormous cosmic voids, regions spanning hundreds of millions of light-years where very little visible matter exists. These are not empty gaps in a simple sense. They are shaped regions, bordered by filaments and clusters, as if carved out by large-scale forces. Some interpretations suggest that dark energy may play a role in driving matter apart, accelerating expansion and influencing how these voids evolve. Rather than being passive emptiness, they appear to be active features of a dynamic system. As the dataset grows, one problem becomes increasingly clear: scale. Euclid is producing information at a level far beyond what human intuition can directly process. Billions of galaxies, each with measurable properties, mapped in 3 dimensions across cosmic time. Patterns exist at multiple scales simultaneously, from small galaxy interactions to the structure of the entire cosmic web. No human mind can hold this entire system at once. Increasingly, interpretation depends on advanced algorithms and artificial intelligence systems capable of detecting structure beyond immediate perception. This creates an unusual situation in modern astronomy. We are no longer simply observing the universe. We are relying on computational systems to help us recognize what we are observing. In a sense, understanding the cosmos has become a collaboration between human reasoning and machine pattern recognition. The unsettling part is not the technology itself, but the implication that reality at this scale may be fundamentally too complex for direct intuition alone. Perhaps the most profound implication of Euclid's early results is how much of the universe remains invisible. Ordinary matter, the stars, planets, gas, and dust we can see, represents only a small fraction of what exists. The rest is dark matter and dark energy, entities we infer only through their effects. Yet these invisible components determine the shape, motion, and evolution of everything we observe. In Euclid's images, this hierarchy becomes visually unavoidable. What we see is secondary to what we cannot. And still, these are only the beginning observations. Euclid has mapped just a tiny fraction of its planned survey. Over the coming years, it will continue scanning the sky, building a progressively more detailed reconstruction of cosmic structure. With each new dataset, the resolution increases, and with it, the number of unanswered questions also grows. Every layer of clarity reveals new complexity underneath. What is emerging is not a universe of simple objects floating in space, but a deeply interconnected system governed by forces we still do not fully understand. Galaxies are not isolated islands. They are nodes in a vast cosmic network. Voids are not empty. They are shaped structures. Even light itself is not simply traveling through space, it is being continuously shaped by the distribution of unseen mass. In the end, Euclid is doing something more than mapping the universe. It is revealing how much of it exists beyond direct perception. The deeper we look, the more the cosmos appears structured by invisible frameworks that define everything we can see. It is not a chaotic universe. It is an ordered one, but the order is built on foundations we have only just begun to recognize. And perhaps the most important realization of all is this: the universe was never simple. We were simply limited in how much of it we could perceive at once. Euclid is not changing what the universe is. It is changing what we are finally able to see.